welcome to day 2 of the workshop on adversarial approaches to machine learning. It's a great pleasure to introduce Manolis Zampetakis, who's a postdoc at UC Berkeley. Take it away.
Thank you very much. Thank you for the invitation. So today I'm going to talk to you about the work that we have done on min-max optimization from the computational complexity to some algorithms for this problem. So I guess you have heard a lot about the motivation of multi-agent optimization and min-max optimization. So I'm going to go very fast through the applications that are related to GANs, adversarial training, markets, or self-driving cars. So all of these applications involve some different optimization than the single objective optimization that we're very familiar with. The problem is that when we try very simple dynamics in this multi-agent optimization, we observe some undesirable behavior very often in practice. And in particular, we might observe that these dynamics converge to limit cycles, or they might even have chaotic behavior. And they do not converge the solutions, the equilibrium of these problems. So the question that we're trying to answer is this due to the methods that we are using, or is this due to the problem? Is the problem inherently more difficult? So my plan for today is to start with a statement of our results, which in order to be better understood, I will also introduce the complexity landscape that is involved in these results. And then my main focus will be to give an impressionistic proof idea of how we get this result in 2 parts. And finally, I will show you how this our complex theoretic result can be used as an inspiration in order to design an algorithm for this problem. So let me start with the statement of the results. So we consider a 2-player zero-sum setting where we have an X player and a Y player, and the X player tries to minimize some objective function F, whereas the Y player tries to maximize this objective function. And in particular, in order to be able to express my results, I would like to compare what we know for the single objective minimization problems compared to min-max optimization problems in the corresponding settings. So we have some function that I will always assume that it's smooth. So the gradient of this function is ellipsis function, and some constraints that are very simple, like convex and convex constraints with easy projections. You can think of these constraints as linear constraints. Okay, so S can be thought of as a linear polytope. Okay, so in the simple setting of both problems, where for minimization we assume that the function f is convex, and for min-max optimization we assume that the function is convex with respect to x and concave with respect to y, then we know that there are polynomial time algorithms that solve both of these problems. So in their simple version, both of these problems look very similar. Now, in many modern applications, though, the function f cannot be assumed to be neither convex nor concave, so it's a non-convex, non-concave function. So what is the solution concept in this case? Definitely, we cannot target global optimality. So global solutions are intractable even for the single objective problem. If you have a non-convex function, it's intractable to find the global optima of this function, even the single objective case. For this reason, we make a relaxation usually, and we target only local solutions. And this relaxation, so yeah. So let me explain. So local solutions in minimization problems is the natural thing that locally, if I move x by just a small amount, I cannot decrease the value of f by a lot. But what local optimality means for min-max optimization? So local optimality for min-max optimization defines what is called the approximate local min-max equilibrium, which essentially says, so, and point x star y star is approximate local min-max equilibrium if by moving x by a small amount, I cannot decrease the value of f by a lot, and by moving y by a small amount, I cannot increase the value of f by a lot. So it's a local saddle point. It looks like a local minimum with respect to x and a local maximum with respect to y. And there are other local solution concepts in these cases, like the local min-max, minimax points, which are have some sequential flavor, so more like local Stackelberg equilibria, and approximate fixed points of gradient descent ascent, which is a solution concept that is pretty much equivalent with this one. Okay, so this is how locally local minimum and the local min-max equilibrium look like. So this relaxation from global solutions to local solutions, it's enough for the minimization problems to bypass the intractability. So if our goal now becomes local solutions, then we know that there are first order methods that can find solutions in polynomial time. Okay, and it has been an open problem whether the same is true for min-max optimization problems as well. So whether relaxing from, in the non-convex non-concave case, whether relaxing from finding global solutions to finding local solutions, it's enough for solving the min-max optimization problem as well. And what we showed last year is that actually this is not possible. So the min-max problems, in min-max optimization, the relaxation from global solutions to local solutions does not save the day. So the problem finding local solutions is still a very difficult problem, an intractable problem. And in the worst case, we'll need exponential many queries to the function value or the gradient value. And when I say exponential, I mean exponential in at least one of the parameters of the problem. And in fact, and this is an unconditional lower bound for any first order method that has access to the function value and the gradient. But in fact, we have also a conditional result that says any algorithm that is first order, second order, or whatever algorithm you can think of will need super polynomial time unless p is equal to ppb. And so unless a complex theoretic assumption breaks. And this is what is called the first version of our theorem, is what's called a black box lower bound, because we only assume that we have access to the values of the function, the gradient at any given point. Whereas this is a white box lower bound. I'm going to explain in a while what this means. This is the first exponential separation between minimization and min-max optimization problems. Okay. So now, yeah, as it's clear from this result, in order to prove our result, we invoke some tools from complexity theory. So I will very briefly introduce the landscape of complexity theory that we are using in order to solve this result, because it will help me describe also some significant parts of the proof. So what is the appropriate complexity theoretic landscape that we need to use for this problem? So what is our problem exactly? First of all, is we're given access to some objective function and its gradient and some parameters epsilon and delta, and would like to find an epsilon comma delta approximate local min-max equilibrium of this objective function. And the access that we can have to F can be either black box or white box. Black box access is the natural thing that at any given point, I am only allowed to evaluate the function value and the gradient value. White box access means that actually you're giving me the whole description of the function. So you're giving me, you can think of this as you're giving me a Python code that evaluates the function. So I don't, information theoretically in the white box version of the problem is easy because I have the whole, I can evaluate the function in any point as many times as I want because I have the full description of the function. But the problem is, given this description of the function, how fast can I find the approximate local min-max equilibrium? So in the white box version, in the black box version of the problem, this is an information theoretic problem. It just talks about how many queries do I need to make to the function in order to compute a local equilibrium. In the white box version of the problem, this is a complexity theoretic, computational complexity problem, because information theoretically I have the whole description of the function, the gradient, in order to find the solution. So what is the, so let's focus on the white box version of the problem. So what is the complexity of this problem one here? Can we hope that this problem is NP hard? And unfortunately, we cannot hope that this problem is NP hard, at least with deterministic reductions, because if this problem is NP hard, then some other complex theoretic assumption will fail. So this is the usual complexity landscape that we think of in combinatorial optimization. So we have the class of polynomial time solvable problems and the class of NP, and these are the hardest problems, the NP complete problems. And our problem cannot be, we don't believe it's NP, and we don't believe it is NP complete. So it lies between P and NP in a class that's called PPAD. And what this class is the class that describes the complexity of finding fixed points of continuous functions. Okay. And our first result is that actually this problem one belongs to this class. So the best that, the hardest that this problem one can be is that it can be PPAD hard. And this is in fact what we saw. So how the problem PPAD, the PPAD class is defined? PPAD class is defined via a graph theoretic lemma that says that every directed graph that has an unbalanced node, it has to have another unbalanced node as well. And the computational problem of given a directed graph, an implicit description of a directed graph and one unbalanced node, and can you find another unbalanced node, is the description of this PPAD class. So now let me turn in another important problem in PPAD that will also help me at the end to describe the algorithm. So this is Sperner's lemma. What is Sperner's lemma? Imagine a two-dimensional grid, n by n grid, and I want to color this grid with three colors, either blue, or red or yellow. And I want to satisfy these boundary conditions. So the colors in the boundary look always like this. But the intermediate nodes, I can color them with any color I want. And what Sperner's lemma says is that no matter how the internal nodes are colored, there always exists a trichromatic triangle. So let's see how we can. So here, for example, these 5 are the trichromatic triangles of this coloring. Very briefly, let's see how we can prove this lemma. So we start from this triangle here on the bottom left corner, and observe that the colors of this triangle are determined just by the boundary conditions. So just because this edge was red and this edge was yellow, we know that this triangle will be colored this way. And we're going to follow a very simple rule. From every triangle, we are going to move to an adjacent triangle, crossing an edge that's going to have the yellow on the left side and the red on the right side. Okay. And since we start with a triangle that has only red and yellow, unless we find a trichromatic triangle, the other triangle that we're going to get in is gonna the remaining vertex will be the red or yellow, and in both cases there is only a single way to go out of this triangle. So no matter how the coloring is, because I have this invariant that I am always in a triangle that is colored with yellow and red, I know that there is always a unique way to go out of this triangle following the rule that I just said. And observe also that I can never enter the same triangle twice. There's only one way in and one way out. And also there is no way to go outside the square with this rule, because there is no yellow-red edge on the boundary that has the yellow on the left. There's no way from inside to go outside. So this path is guaranteed to stay inside, and can never go to the same edge, to the same triangle twice. So it has to stop at some point. And the only stopping condition, the only possible stopping condition is that I find the trichromatic triangle. Okay. And you can use the same idea in order to show that in fact there is an odd number of them. Okay. So now what is the computation? So this is a combinatorial lemma. What is the computational version of this lemma? The computational version of this lemma is that I give you a huge grid with 2 to the n times 2 to the n vertices, and observe that in order to specify just one vertex in this grid, I need 2 times n bits, because I need the one number that describes the position in the x-axis and one number that describes the position in the y-axis. So I assume that if there is a way, there is a program here that, given the coordinates of every vertex, it tells me whether the color of this vertex is yellow, red, or blue. And my goal is, I know that no matter how this program colors the internal nodes, there will be a trichromatic triangle. So the goal is to find such a trichromatic triangle. And again, you can think of 2 possible versions of this problem. One is that I have only black box access to this program. So for every x and y, I can only know what is the color at this specific vertex. And this corresponds to the version of the min-max problem where I have only black box access to the function value and the gradient value. And you can think of also of the white box version of this problem where I give you completely the the program, a full Python code of the program that decides the color of every vertex. And this is a computational version of this problem, the white box access, the white box version. Okay. And yeah, our theorem essentially says that this problem here, this white box problem here, is PPAD complete, and in particular is equivalent to Sperner's, to finding solutions in Sperner's lemma, or computing Nash equilibrium in general games, or computing fixed points of continuous functions. Yeah, yeah, and this is an illustration of what white box access means. And this is an illustration for the black box axis. So now, let me give you an impressionistic idea of how we go from Sperner to our to the min-max optimization problem. So we want to find a min-max optimization problem whose solutions would correspond to the trichromatic triangles of Sperner instance. So we start from a Sperner instance, and we would like to define a game, like a min-max game. So how we do that? We have the max player and the min player. The max player would choose a triangle in this setup, and the min player would choose an edge. Okay, so there is the this is why we call it the edge triangle game. So the one player chooses triangles, the other player chooses edges, and depending on the position of the edge of the edge player with respect to the triangle of the triangle player, we're going to assign to some value. So what is the utility for one player and what is the utility for the other player? And now, instead of giving you the full proof, we're going to observe just that the best response dynamics of this game that we're going to define will exactly traverse these paths of Sperner's lemma. So if this is the setting.
Sorry, let me ask one question. Well, you say the min player chooses the again, the max player
chooses a triangle, and the min player chooses an edge of this triangle.
What is the function?
No, I'm just defining a game.
Okay, sure.
Yeah. So first I will define a game. Yeah. So in this setup, where the triangle player chooses this triangle and the edge player chooses this edge, we're going to say that the max player wins, and the max player is the triangle player. So the triangle player is happy here with this setup, but the edge player is not happy because it is trying to minimize the function value. So when the edge player chooses this edge, then the function value will be -1, and the edge player will be happy. Yeah. So what is the So this is the idea of what we're trying to do, and yeah, very good question. So what's the function value? So the function value is the following. I look from the center of the triangle player, and towards the edge of the edge player. And if I observe from the center that the edge of the edge player has the yellow on the left hand, then the function value will be -1. If it has the yellow on the right hand, the function value will be +1.
The Sperner dynamic preferable edge is -1.
Yeah.
Okay.
So here the edge because the edge of the edge player has the yellow from the center of the triangle, has the yellow on the right hand, looking like this, the function value is +1. Here, because the yellow is on the left, the function value will be -1. So now the triangle player has a local move that will be preferable for him. So he prefers to pick this triangle because now this edge from the center of the triangle has again the yellow on the left side. Okay. And if you play this, if they play local moves, local best response moves, then the only way to stop is to find the trichromatic triangle. Okay. And also,
Just to see in the triangle, in the panchromatic triangle, what's happening? There is no local move for the match player for the triangle. The triangle player can do something.
you see, for the edge player, because the maximum value is -1, but the edge player doesn't have another yellow edge to pick.
The edge player is restricted only in the triangle that the match player will give.
Yeah.
Okay.
And this is where the constraints come from.
Okay.
So the constraints that we have in the min-max optimization, the fact that x, y have to satisfy some constraints, exactly assume that they cannot, so the edge player cannot pick a completely arbitrary edge.
So if the edge player picks the red 2 edge,
Yeah, so this is another constraint. So it will be the constraints are that the edge player will pick the yellow red edge of the triangle that the triangle player picks. Of course, we have to define the function outside of it, but like this definition only works for the. And another important thing is that you can see that here, in order to define the function value of this game, I can do this locally. So I don't need to query. So in order to determine what is the function value when the triangle player plays this triangle and the edge player plays this edge, I only need to look at the colors, 3 colors. I don't need to query the whole grid in order to define my function. So the function value, it's only +1 and -1 and can be determined locally. So that if I can solve the edge triangle game with a few queries, I can solve the Sperner lemma with 3 times the queries that I need for the edge triangle game. And this is a very important feature, and this is exactly the reason that we could not do that with a min-min setting. So you can imagine that you can motivate again the edge triangle to move by decreasing the function value always along the path. But then in order to be able to determine the value of this game, I have to know how far I am on the path. So I have to query a lot of colors in this grid in order, at the end I will have to query the whole grid in order to be able to determine the function value of this game if it was a min-min game. So this is the reason that such a reduction could not work for a min-min setting. So it's a fundamental difference between min-min and min-max optimization.
So that is something like the quantization.
Yeah, it's a potential kind of game. Yeah, it's a potential game. And the problem, it's that you can define such a game, but not in a way that preserves this query complexity or computational complexity. Okay, so the first question then is, okay, what happens if the triangle plays outside the path? So I didn't really describe what happens in this case. We have somehow to extend the function, but with the constraints, we can at least make sure that the edge player will pick an edge of the triangle player. And the second thing that's very important, this is a game, a min-max game in a discrete space. So you can imagine the max player to choose from the set of all possible triangles, which is a discrete space, and the edge player to choose from the set of all possible edges, which is again a discrete space. So you have this product of two discrete spaces, but at the end, what we'd like to do is to define Lipschitz continuous and smooth function. So we have, you can think of this as I have a grid from all the possible combinations between edges and triangles, where I know what the function value should be on these points. And then I need to do some interpolation. And I need to do this interpolation in a smooth way and also in a computationally efficient way. So this leads me to the second part of the proof, which is how you go from a discrete setting like that to a continuous and smooth setting. So what we have, first you can imagine this in 2 dimensions for a while. Like you have a 2-dimensional grid. At every point xi of this grid, I have some desired function value. How can I find a function f, a continuous function f that satisfies all these properties? And this is an easy task. You can just do linear interpolation. The problem is if you do linear interpolation, you end up with a non-smooth function. So this function will have edges and corners like that. So this function does not have a continuous gradient. In order to define a smooth version of this function, we say, okay, apart from deciding the function value on every point of this grid, we also need to assign what are the gradient values of this on this grid. And now we want to find a very smooth way to interpolate among all these conditions. And this is possible in a very general form. So it's what is called the Whitney's theorem in real analysis. It says that no matter how I define a function subspace of the d-dimensional Euclidean space, I can always extend it to a function that is continuous and the first derivative is continuous. In fact, to a C infinity function. The problem is that the construction of Whitney's theorem is not computationally efficient. So in order to decide what is the function value in that point here, I need to use all the values from the whole grid, which is exactly what we were trying to avoid in the first place. So how you can, so what we're looking here is to show what we showed is like a computational efficient version of Whitney's theorem for going from discrete to continuous. And so the first idea that you can have in this setting is that like in order to determine the function value in this point, I will need to query the function values of the corners of the cubelet that this point belongs to. But in high dimensions, even that is not computationally efficient. I cannot query all the corners of the cubelet that my point belongs to because these are 2 to the d. It's impossible even to query all the local points. So this is where the complication starts from. So this idea of interpolating just using the corners of the cube, the hypercube, is not efficient. So what we do is like we take the hypercube and we take a canonical simplicization of the hypercube. One popular way to split the hypercube into simplices is what is called Kunz triangulation. In our setting, we use something that's slightly more complicated, but you can take a simplicization of the hypercube. So you can cut this into simplices. And now say that in every point in this simplex, I'm going to interpolate within the corners of the values and the function values and the gradient values in the corners of this simplex. And these are only d+1. So this is an efficient interpolation in principle. But what becomes, and if you would like only to define a continuous function, then this idea works very well. Like linear interpolation between the corners of the simplexes, using the corners of the simplex, it's an efficient.
We're doing
procedure.
linear interpolation or something better because we need also the gradient, just for the simple.
Yeah. So what I'm saying is linear interpolation would work if you want to get a continuous function, but will not work if you want to have a function that has continuous gradient. And this is a surprisingly difficult problem. So to keep the gradient to be also continuous when we move from, especially inside the cube, when we move from one of the boundaries of the simplex to another simplex. It's exactly because the direction of this hyperplane is very complicated, can be very complicated. This problem, doing this in a computation efficient way, it's a surprisingly different problem. And this is our main contribution. And this part of the proof is to define this, what we call smooth and efficient interpolation coefficients. So what are these coefficients? We assign some coefficients in every corner of the simplex that X belongs to. So this is the simplex that X belongs to. And we assign one coefficient such that this is interpolates between the functions at the corners. So this should be VI. So yeah, this is the gradient that we want at the point P. And this is a convex combination of the functions at the corner. So it has to be the sum of all these coefficients has to be equal to 1, and the value has to be always positive. And unfortunately, I don't have the space to express these coefficients.
Can I ask a question?
Yeah.
So if I understand correctly, PV of X is a partition of unity, right?
I didn't hear you very well.
I said PV of X is a partition of unity, correct?
Yeah.
Okay. So what guarantees you have that the smoothness of PV of X will not violate the global Lipschitz constant constraint for the function that you want to construct?
That's a very good point. Yeah. So we have to make sure. Yeah. So there are some other conditions that they don't write here. So we have to make sure that it's actually easier to construct coefficients that change very, very fast, so that you violate the global Lipschitz condition. Yeah, that's actually a very good point. So we have also to make sure that these coefficients are smooth enough also. So they don't, their derivative will not grow like crazy. So in fact, the derivative of each one of these coefficients, the gradient of each one of these coefficients is only, depends only polynomial in the dimension and not exponential. That's a very good point, yeah. And this construction, as I said, it's very difficult, so I cannot even write it here. But it was hard even to prove that actually these coefficients, we can compute them in polynomial time.
YLP or something else?
No, it's something.
Okay.
It's a bit ad hoc construction. It involves a lot of different kinds of smooth step functions, but yeah.
So the claim is that there is an algorithm.
There is an algorithm. I guess this is what I want to say. Yeah. If I want to get a little bit in more details, I'll need two main definitions, and I don't have the time. But like the bottom line is that there is an algorithm that does this job, and hopefully this is an algorithm that can be used in other settings as well. So in general, it's an algorithm that can be used in order to move from discrete problems. It's a systematic way to move from discrete problems to continuous problems while keeping the derivative also continuous in a computationally efficient way. Again, finally, in the last 2 minutes, I'm going to tell you how from this complexity result, from this idea between the connection between min maximization and Sperner lemma, you can actually define an algorithm that is not going to be efficient because we know we have the intractability result, but at least will satisfy that eventually converges to a solution. So trying to bypass this lower bound, as I said, there are two ways. One of these is what I'm going to describe very briefly in the next slide, which is how to go from to relax the polynomial time convergence in the worst case, and at least have a guarantee of asymptotic convergence. So eventually converges, which is not true for classical gradient descent ascent dynamics because they might converge to limit cycles or they might have chaotic behavior. And another way, which I think will be the topic of the next talk, to bypass this lower bound will be, okay, we said that for minimization problems, for non-convex minimization problems, relaxing from global optimality to local optimality made the problem easier. For min-max optimization, this is not the case. So relaxing from global optimality to local optimality, doesn't seem to be enough. But maybe defining another solution concept, relaxing the local optimality a little bit more, is what will make this problem to be tractable. And again, finding a solution concept that we can converge to it, it's a very important thing because again, the gradient descent ascent dynamics may not converge to anything. So finding reasonable solution concepts beyond just locality, it's another way to bypass this level. Okay, so very briefly, in 1 minute, what is our algorithm that we devise? So observe that while proving Sperner's lemma, I explained to you how you can move in this square in order to find the trichromatic triangle. And now imagine what we did is like, imagine that you take the discretization of Sperner's lemma in this correspondence between min maximization and Sperner's lemma to go to 0. And we look at the continuous curve that comes out of this. And this is in fact a second order dynamics. It's very interesting that it becomes, as delta goes to 0, this becomes a second order dynamics, and which has the guarantee that eventually will converge to an equilibrium point. So these dynamics, just because the Sperner dynamics, we know that it will converge to a trichromatic solution. If we take delta to go to 0, we expect these dynamics, it's not trivial to prove, but like we expect that these dynamics will converge to a solution. And very briefly, how these dynamics would look like. So the first step, the starting point of these dynamics is to search, let's say that we have the 0, 1 squared here, to search along the y equals to 0, sorry, x equals to 0, sorry, this is x equals to axis, and find the local maximum, this point here. And then these are the dynamics that we, so at every step, we make the tangent line is described with respect to this direction. And what this direction makes sure is, first of all, that the maximum player is always happy. So we start from a place where the maximum player is happy because it's a local maximum with respect to y. So it's we make sure that the maximum player will remain happy. And also the most important property, we make sure, as in the Sperner's lemma, that this dynamics will never go back to the same point again. So this is why these dynamics will have to exhaust the space and finally reach a solution. Yeah. And yeah, so you our intractability result and hopefully a brief description of and also a brief description of our proof and how we get this intuition from the complexity to build a second order algorithm. So what are the main open questions? One question is how to solve the corresponding lower bound with product constraints. what happens in the unconstrained case, which we are right now, we have a first answer about that. And what are the conditions under which the dynamics that I very briefly showed you at the end converge very fast. Yeah, that's it. Thank you.
About the solution concept. You have your main theorem. It's about what is the solution concept that you are. Is that local minimum? Local.
Yeah, it's a local minimum with respect to x and the local maximum with respect to y.
But for minimization, how do you get the local?
It's an approximate local. So it's labeled this.
Okay, but for example, gradient descent is stationary convert.
Yeah. So stationary points, you can think of them as approximate. So if you move a little bit, if the gradient is approximately 0, and you move the x layer by a small amount, then you don't expect the function value to change by 1 variance.
But is it like for like the class result of Kabad, finding the local minimum in constraint? Is that the part? Checking even the local optimal.
So this is for checking exact local optimum.
Okay.
So if I give you a point and I want you to tell me whether and it's not a local optimum, just whether it's a second order stationary point still. So it could be.
So what is the exact definition that you're using?
So this result is that if I give you an x and I want to check whether the Hessian of x is exactly positive definite, this is amplified. This doesn't mean that it's a local optimum because you can think of the x cubed case. Still, this is a not local optimum, it's a second order stationary point. So, but if you allow here some error, so you make it approximate local minimum, then it's on track. So this result is just about
But it should be with respect to certain cone. So it's like it's co-positivity problem in minimization.
Right.
It's still difficult.
Yeah, but if you allow approximation error,
Okay.
if you allow even a small approximation error, like an epsilon, then in polynomial you want to write sometimes with epsilon.
Your construction is there a coupling between constraints of x and y?
Yeah. So these are coupled constraints. Yeah. So we have the mean with x plus respect to y of f of x comma y, such that x comma y belong to some set. So the whole record belongs to some set.
If they are decoupled, is it?
If they were decoupled, this is the open problem that I mentioned.
Oh,
This for product constraints.
oh okay.
But this is very natural to happen, especially in game theoretic settings, because like even in tic-tac-toe, you don't have the strategy of one player restricts the set of possible strategies of the other player. This happens a lot in market building. So these are very natural constraints, but it's an open problem whether the same holds for product constraints.
So I'm trying a little bit to understand about the dynamics at the end. Do we have again the coupling constraint? Yes or no?
Yeah, we can have the coupling constraints as well. Here I described it for the product constraints. We can have even for the coupling constraints as well.
But it holds also for product constraint.
The product constraints is a special case.
Okay. The lower bounds, even for the black box, are for the constraint set.
Yeah.
Okay. I think I'm covered.
Okay.
All right, so any last questions?
Probably one last one. Yeah, sure. Can we describe a little bit, like, as a takeaway, what is the routine, the guarantee of the smoothing routine that you have? I give you a discontinuous function. What you can return me?
I can return to you a continuous function, a smooth function that agrees on your function in the grid points.
Okay, and the gradient of, okay, if I give you, my question actually was, can you do that for higher gradients like
Yeah,
Hessian?
so in principle, you could do that. You can even have a C infinity function. It's just that it becomes a little bit more difficult to solve the computation. I mean, in a mathematical way, you can have a C infinity function just because of Witness theorem, right? So, but when proving the computational complexity, we were able to only solve the first derivative, the continuity of the first derivative. We have it's very natural from our construction to guess what is the construction even for higher order, so even for say infinity. It's just that the computational complexity, you need to reprove computational complexity.
Thank you very much.
All right, so let's thank Manolis again. We'll see you back in 20 minutes.